So I wanted to spend a minute introducing and talking about transformer neural networks. The development of transformers was a path. So the first part of the path was, although naively we said, okay, there are recurrent neural networks, they maintain this hidden real vector state that captures some of the past. That means everything we know about the past has to be sort of crammed into this one vector that's carried forward over time. And so people developed the idea, initially actually in slightly different context from machine translation, where you were looking between a source to what you were then generating as your translation, but we can just use it here for one language of saying, well, maybe instead we should use the hidden key mainly as a kind of a key like a hash key that will let us look back in the past to see which parts of the past are most relevant to help us generate the next word. And so the way that that's being done is you're calculating some kind of similarity score between your hidden state and past hidden states. Based on that, you're putting a weighting over the past hidden states depending on how similar they are to your hash key. And then you're using those weightings to produce a weighted average of past hidden states. And that weighted average context vector is then being fed into the generation of the next word, which is generated in the same kind of a way from a softmax distribution. So then in 2017, Ashish Vaswani and a whole bunch of colleagues at Google suggested the slightly radical idea of, well, we're making so much use of attention, maybe we could just build a model that's all about attention and gets rid of the recurrent neural network altogether. And that has actually enormous computational advantages because recurrent neural networks have always been really unfriendly to that awesome parallel computation that these great GPUs that people go on about always talk about. You know, GPUs in a good period, but they've been really good for things like convnets and vision because you can do everything in parallel, whereas a recurrent model isn't parallelizable to the same degree. So if we get rid of the recurrence, that's great for computation. And well, the suggestion was that we could start making a very deep model, as again, people do in vision. And if we make a very deep model with a succession of layers of attention, then that will allow us to do a certain amount of lateral information transfer in depth rather than in horizontal sequence. And so this was the idea of the transformer model. It was then an all-attention model. And in particular, the most famous at the moment attention model that's been used for natural language processing is this BERT model, bidirectional encoder representations from transformers. And so the idea of it is that we're going to pre-train a huge transformer by doing word prediction with it. And then that will give us kind of a general, I understand a human language ability, which we'll then be able to use for different particular tasks. And so the way this model is being trained is that you're taking sentences, the man went to the store to buy a gallon of milk, and you're blanking out a few of the words, and you're wanting to train a transformer model to predict those words. So it's going to use attention to context to try and predict the words. So this is then sort of self-attention in a mask sequence model. So we're doing the same kind of attention computation of calculating attention scores in context to get an attention distribution and attention output. So starting off, that mask has less information, right? Because it's not actually something that's being calculated recurrently, storing everything that happened beforehand. All it knows is I'm a missing word. But as we head up the transformer stack, we'll start to get more information. And then the second crucial innovation was to say, well, the basic model just had one similarity calculation as to how similar things were, and then one sort of weighting of where to pay attention. But if we're wanting to generate, there are probably sort of lots of relevant words in context, and they're relevant in lots of different ways and for lots of different reasons. So what we'd really like to be able to do is have lots of attention, so we can attend to one word because it expresses the theme of the sentence, attend to another word because it's a verb that is the main verb of the sentence, attend to a third word because it's possessive, and we can look in lots of places. So in the BERT model, we both have lots of attention heads, either 12 or 24 depending on size, and lots of layers in the model so that we're applying attention over and over again and updating our representations as we go. So we're going to start off by training a BERT model just to predict words on a humongous amount of text, where we're in this sort of space of billion or more words of text most of the time. And then to do well on tasks, we're then going to say, okay, there's some particular tasks we want to do, parsing, named entity recognition, sentiment, whatever it is. We can then take this pre-trained model and just fine-tune it a little to work well on a task. And this BERT recipe has proven to be just sort of super successful for NLP, and so now everybody uses it everywhere for everything. And if you want to be competitive at winning bake-off tasks, you sort of have to. So to give just one example, here's question answering. So in question answering, there's a passage of text, there's a question, which team won Super Bowl 50, and you're meant to look through the passage of text and find the answer, which is here. Not really showing up on this slide, the Denver Broncos. And so here we were back in 2017. It was already the case that people had shown that deep learning neural network models worked for this way, way better than conventional machine learning models like the logistic regression at the bottom, but we're still sort of well below human performance. If we skip ahead, to early 2019, after BERT was out, we were then in this situation that the numbers were much, much better again on the results, getting close to human beings. And if you wanted to be anywhere in the top 20 places on the leaderboard, you had to be using BERT in your model. And then if we skip forward again to almost today, well, luckily there's a little bit more diversity back in the world now, but it's essentially only because other groups have built similar kinds of BERT-like models. And so we also have Albert and XLNet and Roberta as sort of different models of the same structure, which are also proving successful.